Awesome. So thank you everyone for joining the One World Math of Machine Learning seminar today. It's my great pleasure to introduce Minshuo Chen. Minshuo's assistant professor at in Industrial Engineering and Management Science at Northwestern University. Prior to joining Northwestern, he obtained his PhD at Georgia Tech, and then went on to do a postdoc as a research scholar at Princeton. And since then has been working a lot on topics related to generative modeling, from both the mathematical and methodological development and trying to understand how they work. And today he's going to be talking to us about one of those generative models, diffusion models in particular. So Minshu, please take it away.
Well, thank you. Thank you so much for the kind invitation and for the introduction. So, it's nice also to meet you online. And today I'm talking about I will say, a emergent application of diffusion models in decision making. And we will talk about how we can steer diffusion models generation to how to control when to use diffusion models to generate actions for real-time decision making. So this will be a joint work with my two students and also some wonderful collaborators at Northwestern and also Georgia Tech. I think I don't need to convince you that the generative AI is revolutionize the AI development trajectory. I think in the start of the century, people are mostly focusing on something called discriminative AI, where the goal is try to come up with like very powerful model architectures and try to do tasks like classification, regression, those sort of things. But the landscape actually changed quite a lot starting from the year 2013, where this idea of deep generative AI emerged. And ever since, I think the development, especially in the recent years, is skyrocketing. So this is kind of like a little bit outdated figure of what is the trajectory of deep generative AI, although I think the time stops at 2023, but in the past 2 to 3 years, there's a lot of new things happening. And I think it's also kind of like a little bit stressing for me because it's hard to keep up with everything that is happening inside the field. So this is kind of like also a little bit obsolete joke about math, and this is a joke that I referred to almost every morning when I was on the job market because I feel a little bit like depressed, so I need some joke to cheer me up. But today I think what I will talk about is not about some like very generic application of deep generative AI or its underneath theories. We will particularly focusing on the integration of deep generative AI with real-time decision making. So the typical model we will consider is a reinforcement learning or a decision model that consists with an agent and an interactive environment. So the goal here is the agent will interact with the environment by taking actions, and the environment will return some feedback to the agent so that the agent can make wise decisions at each time step. Well, a very classical deep reinforcement learning methodology is try to parameterize how agent execute actions by a policy class. And the policy class is using a policy network that will try to predict what is the mean and variance of a Gaussian distribution. So this is kind of like a very old-fashioned and also powerful method that try to recommend actions given the current state from a sampled point from a Gaussian distribution. This methodology has been driven many of the powerful and also brainstorming applications like AlphaGo, which gives superhuman performances, and also it has been very helpful in designing autonomous driving systems. Although we cannot like credit all the powers to those classical deep learning reinforcement learning methodologies, but these are the very core methodologies that have driven these advances. However, there's actually a very big problem with this classical deep reinforcement learning method because we are parameterizing the policy using a Gaussian distribution. So remember, Gaussian distribution is a unimodal distribution. Therefore, most of the situations, the policy will recommend some type of agreed or some type of unimodal behavior. But in many of the reality applications, we are considering many multimodal or many feasible solutions to one task. Therefore, I think this is an idea coming from the paper, a seminal paper, which called the diffusion policy. And this is trying to replace the Gaussian policy network with a diffusion model. So this type of advantage is immediate if we look at what is the capability of diffusion models. Well, diffusion models can generate actions. It is not limited by generating unimodal actions. It can capture very complex and also high-dimensional distributions. Therefore, on the very superficial level, replacing the Gaussian policy network by a diffusion model may seem to heavily generalize the capability of the agent in many of the complex environment. And this is exactly true if you look at this application where a robot arm controlled by a diffusion policy can make a pizza for us. And there are also other type of very successful examples of using diffusion models to control dual arms. And this Dyna is a robotic startup company which tries to make robots that can fold napkins. And the prototypical model has been deployed in real restaurants in the Los Angeles area. So with this type of replacement, introducing diffusion models into decision making, people are hoping to develop something called generalist robots. And this generalist robots can actually integrate like language models and also decision-making systems so that the robot can learn and also can execute very complicated and step by step or learning new things step by step. However, there's actually very huge challenge in order to make diffusion models as a very reliable and real-time policymaker. And the unique features underneath using diffusion models for decision making is, suppose this is the evolution of a physical Markov decision process. So at the time h, I have a state which is sh. And given this state, a diffusion model will try to generate actions following this chain. And this chain starts from a Gaussian distribution and then gradually denoising so that we have a clean action that is generated. And we will denote that the clean action, which is denoted as AH, sampled from a distribution called pi of AH given the current state SH. So then AH will be executed in this environment SH, and we will call this type of generation using a diffusion model starting from the Gaussian noise to a clean action being one inference call. And inside this one inference call, there are multiple transition steps. And each of the transition steps inside the diffusion model will be typically driven by a very large neural network. For example, this is the UNet architecture, and nowadays people are also using transformers to drive one step of the transformation. And a diffusion model typically consists of 20 to 50 steps when we use the vanilla implementation. However, there are many like faster generation schemes that can reduce the number, but I think still diffusion models need some type of transition steps so that we can generate a action. So this will actually give us one problem. The problem is because we are generating actions step by step, it is relatively difficult to get what is the likelihood function of your generated action. So this is completely different compared to the Gaussian policy. Gaussian policy, because we parameterize it as a Gaussian distribution, so it is very straightforward to get what is the likelihood given the action and the current state. However, diffusion models is a model that can generate realistic actions, but it does not have a very easy access to the likelihood function. So this will be a issue when we try to make the diffusion model or try to make diffusion models to recommend actions that can maximize the accumulative reward. And there's actually another issue, and this issue is because we are generating actions by a sequential process, and this sequential process takes some time. Well, this is not as I sample one point from a Gaussian distribution that can almost happen immediately. But in the diffusion model, you are generating something starting from a Gaussian distribution and then use a very large network to transform the sample from the Gaussian distribution. Therefore, it takes some time. And this time can intervene with the physical time. For example, here, if I'm at physical time h, and I call a diffusion model to generate an action, the reality is the generated action will return to me at time h plus delta. And this delta is almost non-negligible because the size of the diffusion model. This type of inference latency will cause a very complicated interacting protocol if we want to deploy the diffusion models as a policy. There's one well-known failure example of the diffusion models for making actions subject to the inference delay. Suppose right now we are at step A3. So here time is 3. And if I start the inference, and suppose the diffusion model will predict that in order to circumvent the collision to the obstacle, I need to go the red route. So the red route is a perfect avoidance to the obstacle. However, because I'm subjected to the inference latency, I cannot get the immediate action, for example, A4, until I'm at time h equal to 10. And during the time between A3 and A10, I'm just acting something that may be stored by some action buffer, or I just do some type of random guess. Or sometimes maybe we can wait. But the real situation is if I happen to choose that, okay, I need to circumvent the obstacle going the black route, then at time h equal to 10, the predicted actions, which is the red one, returns to me. So I execute according to what is predicted by the red curve. Then a disaster will happen. I will follow this type of brown curve, and then I will hit the obstacle. So this is a situation that is caused by the inference latency because the state that is used for generate the actions is not the state that the action might be executed. Okay, so these features are actually calling for many new development and also new analysis in order to make diffusion models a powerful and a flexible model try to make reasonable and reliable actions in the real-time decision-making system. So what we will take in this talk is we will try to use one shared objective, but we will develop two sets of methodologies to address those unique features in diffusion models for decision making. So the overall reward maximization objective is written as by taking actions AH, I want to maximize the accumulative reward, which is denoted by RH in the real task. Maybe you are wondering, okay, this is the most weird and ugliest expectation I have ever seen because it's like a alien distance between this expectation and the summation of the terms. In fact, there are two expectations that we should consider. The first expectation is I want to make wise actions. So this P sub action denotes what is the action recommended by a diffusion model. And there's another expectation, and this expectation is the inference control. So the inference control actually should take the inference latency into account, and it will control when we should start a new action prediction, given that the action will only return after some type of gap. Okay, so the goal of the action policy P sub action is try to do reward maximization, and to be more specific, if we are familiar with the Markov decision process, then we can use the Q function to denote or the measure if the action at an intermediate step is good or not. Therefore, the goal of the action policy is try to optimize some Q function measuring the accumulative reward given some type of maybe very bad base policies or starting from the scratch. And the second thing is we will also try to learn an inference policy. And this inference policy is very important because it is a meta control policy. So remember in the previous failure example of hitting the obstacle, even if we have a perfect action policy, the inference latency can still make the action policy not a good one in the real development. Therefore, the inference policy is try to control when we should start to generate, for example, a new sequence of actions given the current state sh. Here, the orange dot sh is the time that we will generate new actions, but the green dot says, okay, we don't need to generate new actions because this state is safe or this state is not informative. Right, so the outline of this talk will be the following. So we will try to introduce what is the basics of diffusion models and especially consider what is a conditional diffusion model, because in decision making, we always generate actions conditioned on the current information, for example, the state, or some past executed actions, or some stored future actions. And then we will provide two sets of resolutions to the two unique features. Number one is we will try to develop a training-free reward steering method that can make a diffusion model to generate high Q-valued actions. And the second one is we will develop a meta-control methodology or policy depending on a semi-Markov decision process formulation to give a inference timing control so that we can make the diffusion models to be a responsive and reliable action generation in real time. So let me pause a little bit to see if there's any questions. Okay, perfect. Right. So the first part is about the score-based diffusion models. So maybe I don't need to spend like a long time introducing what is a diffusion model, and I bet many of the audiences will already know quite well about the diffusion models. So here, let me just try to introduce some type of notations, and also I'm using a continuous time description of the diffusion models. Therefore, we are using stochastic differential equations. But instead, what is really happening is the forward process is try to make your data distribution looking like a noise distribution. And the way to transform it is try to shrink the data magnitude and then add some Gaussian noise. So this is a very simple to understand process. So what we are doing is we will push every data point towards the origin, and then at each data point, we are adding larger and larger Gaussian noise. So mathematically speaking, you can write this process simply as this stochastic differential forward equation. So dxt equal to minus 1/2 xt dt plus dwt. And of course, I'm taking a very simple way to write this OU process because I'm making the coefficient minus 1/2 to be fixed, not time dependent. And in many of the implementations, you can make it time dependent. So the magical thing about this forward process to add noise to the data is it is reversible. So in the reverse process, we are kind of like flip the time. So the starting point now becomes the noise distribution, and then the end point becomes the data distribution. So in order to make this transition possible, we are using something called the score function. And the score function is the gradient of log marginal density functions when you try to add noise to your data distribution. So the marginal density function is denoted as P capital T minus small t. So in the classical literature, there's a rigorous proof saying that the forward process and the backward process are nicely coupled, and the corresponding marginal distributions are matched. Okay. So graphically speaking, we can draw this type of correspondence, although in the approximate sense. So the forward process transforms data distribution into noise distribution, and the backward process doing it in the reverse order. So the distributions are matched at the corresponding times. So there's one thing I want to emphasize. The diffusion model is usually considered as a stochastic model. Therefore, it is not trying to reproduce every data point. So everything we are describing here is a alignment in the distributional sense. So the initial distribution will match the terminal distribution of the backward process, and the terminal distribution will match the initial distribution of the backward process being Gaussian. So the training of the diffusion model is trying to minimize some type of quadratic loss. And inside this quadratic loss, we are using a neural network S of xtt to map what is the target score function gradient log pt. Although I'm cheating here because gradient log pt xt is unknown to us. Therefore, in the literature, there's a very seminal work that try to rewrite this training loss into an equivalent form so that it is directly implementable. And the idea is try to use the integration by parts and then replace the score function by a conditional version. So after we train the score function S, we will try to use it to generate samples. And here I'm using a very simple way to generate samples. We're considering a piecewise linear approximation to the backward stochastic differential equation. So here we are considering we are partition the overall time interval into smaller pieces, tk to tk plus 1. And on each of the smaller time interval, we will fix the score function S at the starting point xtk and time tk, but we keep the linear term and the Brownian motion term to be evolving as time evolves. So this one is actually mathematically explicitly solvable. So you can write explicitly what is the update in this smaller interval tk to tk plus 1, because the drift term here is a linear term. Okay, so everything introduced in the past 3 slides are about if I have a distribution, then I want to capture the distribution using a diffusion model. We haven't talked about whether we are able to add some conditional information to the generation process. So here we are trying to transit from only generating samples from an unconditional distribution to a conditional distribution. So the conditioning here is abstracted as a Y. So Y can be a label, Y can be a text description, and Y can be a state, Y can be other actions when we talk about decision making. So diffusion model actually provides a very simple way to add conditional informations. And it has many successful examples in cross-domain applications like in image generation or biochemical molecule generation tasks. So the idea of getting conditional samples from a diffusion model is we will try to replace the score function by a conditional score function. So the only difference between a score function and a conditional score function is in the conditional score function, we have a label y. So this label y will not be corrupted, meaning that we will never add noise to the label. So this y will keep through all the noisy states when we try to generate samples. Of course, you were wondering, okay, now how can you get the conditional score function? Of course, this is actually the topic today. Then in literature, there's a large set of methodologies that try to get what is the conditional score function. But of course, the bottom line of getting a conditional score function is we don't want to estimate the conditional score function from scratch. The reason is diffusion model is usually a data-hungry model. It requires to train the model on a large collection of data points. Therefore, the best practice to get a conditional score function is we want to relate it to a unconditional score function, because unconditional score function is considered as a pre-trained model, and then using the pre-trained model, we can scalably adjust or adapt the diffusion model to generate conditional samples. Okay, so let me also pause a little bit here to see if there's any questions. Okay, cool. Right, so then we will try to talk about the first part. The first part is how can we generate actions that will give us large reward? So this is exactly the question of how can I try to do conditional generation so that the generated samples will give us a very large Q value or the accumulative reward. So a very traditional way, for example, policy optimization, can be viewed as some type of optimization methods. And the goal is try to optimize a objective function. And how we do the optimization is we start with some guess of the actions or a parameterization of the actions, and then we will update the parameters that parameterize the policy class. However, in diffusion models, we will take a very different perspective. We will view this as a sampling problem. So the sampling problem is try to generate new samples, actions, AH, so that this generated action, AH, can maximize the Q function. So this is not like we are doing some like path following or trajectory following method in the traditional optimization literature. We are directly trying to generate a solution to the Q function that it will be maximized. So conceptually speaking, we can do this following this type of methodologies. So here I'm using X to denote a abstract generated things, and in decision making, we consider this X as the generated actions. So here we start from a Gaussian distribution, which is x0, and then we follow the backward process of a diffusion model so that it can generate a lot of different points denoted here as those like black dots. So in many of the situations, we will try to select those generated xt so that it falls into a very good region. And in the decision-making problem, we will choose this region to the large Q function region, indicating that, okay, these are the good actions that can give us a very large reward. So the selection can be made possible by I'm getting a indicator function, and the indicator function tells me whether my generated action xt will belongs to the desired region epsilon or E. And this introduces a tilted terminal distribution, which is written as pt of xt given the conditioning E, which is proportional to the unconditioned generation times the selection, which is the indicator of your generated sample falls into the good region. So this is very similar to the well-known like rejection sampling. However, as you know that rejection sampling or other type of direct sampling method can be fairly inefficient. But why it is inefficient, or how should we interpret this inefficiency in the diffusion models? So remember here, we are just considering a diffusion model as an end-to-end system. End-to-end means we start from some noise distribution and then we end up with data points inside a generated space. And then we will select those generated points that has a very good property. However, what we can actually control is the generation from x0 to xt is following a stochastic process defined by the backward process of the diffusion model. So we can actually intervene each step of the generation. We don't need to rely on getting the terminal data point. We can adjust the generating pathway in the very early stage because it allows us to adjust each step of the generation by modifying the score function. So this is exactly the idea of doing the reward steering in the diffusion model regime. We are not doing a pure selection on the terminal generated samples, but we are doing step-by-step adjustment. So the idea is now, instead of just looking at a tilted terminal distribution, we are defining a collection of tilted intermediate distributions. And the intermediate distribution now is written as Pt of xt given the desired condition, which is set to be proportional again in the similar format of the tilted terminal distribution, a unconditioned intermediate distribution times another selection, ht of xt. Therefore, the question here is, how can we choose this ht of xt? So let me try to give you some type of intuitive understanding of how can we choose this ht of xt. So here xt is an intermediate state, and this intermediate state is obtained starting from x0, but this intermediate state will end up with a collection of generated samples, x capital T. So we know that the good region E is here, so we know that if we try to generate starting from x small t, then we have some fraction of the samples falls into the space of E. Therefore, this function h of txt should help us to bias the generation starting from xt towards those trajectories identified by those like the upper two trajectories that will end up in the desired region of E. However, there's other type of situations. For example, I'm considering a different point xt prime, and this xt prime will end up with generated samples that belongs to this point E with a smaller probability because many of the other generated data points starting from xt prime will be outside of this desired region E. Therefore, in this intuitive sense, we should assign this xt a higher weight. And the reason is because xt can generate many good points that belongs to the set E, but this xt prime may be less favorable because it has a lower probability of generating points that belongs to the set of E. Therefore, we can define a h function in the following form. So we are looking at the expectation if we start from xt equal to x, and then we try to ask ourselves how many data points we'll end up with in the good situation. And the good situation is measured by this desired terminal condition h of capital T xt. And in the previous example, we can just take this h of capital T xt as the indicator function, telling us whether xt belongs to the set of the E. Okay, so this is more or less like a reweighting, but in fact, it is internally connected to the stochastic control idea. So this h of xt will actually construct a very optimal probability path if we define this pt of xt given E in this type of form. And this optimality is justified by the KR divergence between this pt of xt given E to the unconditioned distribution of pt of xt. So essentially this says if we choose this ht of x in this type of simple form, then this adjusted path pt of xt given E will give us samples that belongs to the set E, but at the same time, it will stay as close as possible to the unconditioned original generation process. So this is kind of like very important because this type of closeness or optimality can allow us to adjust the original generation process with a relatively minimal efforts. So up until now, I think I try to deliver what is the intuition that we can modify the generation process by introducing some reweighting mechanism in all the intermediate steps of diffusion models. But what we haven't talked about is how can we use this type of information to adjust the score function? Because in diffusion models, we have no access to this intermediate density functions. We only have access to the score function or the conditional score function. Therefore, the gap here is how can we make this HTX possible, being possibly implemented by a adjusted score function. So the score function now is defined by the gradient of log density function, as introduced before. So a very easy calculation will give us the following equation. So the score function of the conditional density function is the sum of the two terms. The first one is the unconditional score function, and the second one is a correction term. And that correction term is relevant to the weighting function h that we have introduced before. Therefore, we call this function the Doob's guidance because this h function is also known as Doob's h function in the literature. So in all the following discussions, we were talking about how can we calculate this Doob guidance term. And this Doob guidance term is a gradient of log ht of x. Therefore, we can just write it as a fraction, and this fraction will give us gradient of h divided by h function itself. And here h is a expectation. So expectation is taking with respect to the diffusion generation process, and the starting point is at time t, and the starting location is x. So maybe a naive way is try to say that, okay, because I have an expectation, so I can naively approximate this expectation by Monte Carlo rollouts, then I average it. Of course, this is a very viable methodology. However, this very viable methodology only works for h function. It does not directly work for this gradient of h function. Because this gradient of h function involves taking gradient with respect to this conditional information inside the definition of the h function. So what is the way out? Well, so our idea is the following. So we will write this gradient of h function as a integration by its definition. So what we are doing is we just replace this conditional expectation by a integration. And then we observe that the gradient is only taking with respect to x. Therefore, we can move this gradient inside the integration so that we take gradient with respect to this type of transition probability defined by the diffusion model. Now we realize that because diffusion model does not give us a tractable likelihood, which means we don't know what is ptk of x capital T given xtk equal to x at step k in the discrete sample generation process. However, we have a very good property of a diffusion model when we try to generate samples. Remember that we said in the sample generation process, we will consider a time discretization of the process. And at each small interval tk to tk plus 1, the score function is actually fixed and it will be evaluated at the starting point of the interval. Therefore, at each smaller interval, we have a explicit formula for what is the transition from the time tk to time tk plus 1. And we will exactly use this type of formula to rewrite what is this ptk of x capital T given xtk. We will write it using the Markovian property of the sample generation. So the first step is try to evolve xtk to xtk plus 1, and then we will evolve xtk plus 1 to xtk plus 2. And there's another good news. The good news is this ptk of xtk plus 1 given xtk is a Gaussian density. The reason is it is defined by the backward stochastic differential equation because we fix the drift to be a linear term. Therefore, the explicit solution will tell us this density function is a Gaussian density function. So now everything seems to be resolved because now we write what is the transition from xtk to x capital T by a product of Gaussian density functions, and we know explicitly its analytical form so that we can take a gradient in closed form too. And there's another very good property of this type of methodology because the gradient is only taken with respect to the transition densities. We are not requiring any differentiability on the terminal conditions encoded by this h function. Remember, in our example, when we take an h function to be indicator function, then if we have a gradient in front of the h function, then we are in a huge trouble. But now we are only taking gradient with respect to the per step transitions, which is Gaussian. Okay, so this gives us this type of a prototypical algorithm. So we can implement this Doob guidance into a diffusion model. And the idea is we will at each step try to compute what is the correction gradient of log h by roll out trajectories. And we denote the number of roll outs to be capital M. And given the capital M trajectories, we can separately approximate the denominator and the numerator of the gradient log h so that we can compute it exactly. And then we can do a adjusted sample generation using this type of adjusted gradient log PTK score function. So there's a very nice approximation guarantee saying that if we have capital M rollouts, then the approximation to this gradient of log h Doob guidance term will converge at the scale of capital M to the power of 1/6. Okay. So why we call this prototypical algorithm? The reason is this algorithm is actually still relatively expensive to implement. And the expensive part comes from this. We need to roll out the capital M sample generation trajectories. And again, we said diffusion model is kind of like a massive model. And in order to generate samples, it takes time, it takes computational resources. Therefore, in order to do one step correction, we need a capital M rollouts. Then if we want to correct all the generation process, we need a lot of rollouts and it will be extremely slow and expensive. Therefore, we have a practical approximation to the M rollouts. So instead of doing step-by-step rollouts, we will replace those rollouts by a one-step rollout. And this is possible if we use the 2D's formula that can directly relate what is the terminal generated samples given the current state in the diffusion generation process when we are evaluating at time tk. So the details of this tedious formula and how we do this type of generation is a little bit complicated. So you can check our paper. However, what we can achieve here is we will replace M rollouts by multiple step generation by only a one step rollout. So this is very important because one-step rollout almost adds no computational overhead to the original sample generation process. Okay. So these are the empirical results that we implemented using our developed Doob guidance method to steer the generation towards large reward regions. So we are not only talking about considering the decision making, but we also tested on the image generation tasks. Without any type of Doob guidance, the generated distribution will behave like this, and the y-axis is trying to measure the very abstract aesthetic quality of the generated image. And by adding Doob guidance with many tunable parameters, we can see that the average generated reward will bias towards high reward regions. And so here you can see some image examples, although I think maybe this is slightly difficult to observe, but upper row is without any guidance and the lower row is with guidance. So the upper row has some type of visible hallucination or distortion in, for example, the face of the dog or in the tongue of the dog. However, in the lower row, we can see that the generation is kind of like falling quite naturally with the a real image of a dog. So we also test our method on the D4 reinforcement learning locomotion tasks, which is a physical-based locomotion tasks widely used for testing conditional generation or reward steering for diffusion policies. So our method beat many of the existing state-of-the-art methods. One good thing about our methodology is we almost introduce like no computational and generation time overhead compared to the original generation process. You will see that the improvement using our practical algorithm compared to with the prototypical algorithm is pretty huge. Okay, so let me also pause a little bit to see if there's any questions. Okay, so if not, then let's move on to the second part, which is talking about how we control the inference when we have inference latency. So remember this figure. So a diffusion policy will generate actions after some latency. So in many of the practical implementations, we will have this very complicated action buffer and the trunk prediction mechanism. So action buffer says because the action generation is delayed, therefore we need to store some backup actions so that we can execute if there's no like new actions returned by the diffusion model. So this action buffer is denoted by B of h at the time h, and it consists of a lot of like future actions that can tell what to execute if diffusion model is still in the process of generating actions. And then action trunk actually means instead of generating only one action, we are generating a sequence of actions, and the sequence of actions has a length capital L. So this is also compatible with the action buffer because if we generate a sequence of actions, then we have the freedom to choose when we can generate the next sequence because the sequence of actions can guide the agent to execute when the real environment evolves. So there's a very important failure example of wrong inference timing versus a good inference timing. In this environment, you will see that there are two obstacles, and the goal is try to reach the destination but avoid collision to the obstacle. So this purple circled regions are the regions that we observe the obstacle, and these are the critical time that we need to predict what we should execute to avoid the collision. So missing this critical moment can lead to very disastrous consequences, like a hit into this obstacle. However, if we start our action generation exactly on these critical moment, then we can very wisely avoid the collision to these obstacles and reach the final destination. So therefore, in order to control when we try to generate the actions, we will use this develop this semi-Markov decision process formulation. So the idea is now at each current physical state, SH, we will summarize all the information that we have. And this summarization consists of what is the current state, what is the action buffer, and what is the status of last inference launching. Inference launching means when diffusion models are trying to predict a sequence of new actions. So each state can be summarized into a meta state or the augmented state. Therefore, the inference control or the inference timing is try to decide on each of those augmented state whether we want to start a new action generation process or we will just wait until more critical information is reviewed and we will do a new generation at some later step. So now observe that if we start a action generation, it will last for several steps, and the gap is denoted as this delta. And in between this generation process, we cannot like interrupt the diffusion model to generate actions, and we can also not start a new action generation task in in this diffusion model. What we can do is we will only wait until the generated action return to us. Therefore, the real gap between like non-trivial steps that we can decide whether we want to wait or make a new inference, new action generation is like non-even, because maybe at time h the generation takes delta steps, and at time h+1 the generation will take another delta prime steps. Therefore, the real gap between non-trivial decision state in the augmented states is uneven in the physical time. And this actually validates the idea of a semi-Markov decision process formulation. So we will distinguish the real time h with the decision stage k. And usually decision stage k will occupy many of the physical states because of the inference latency. So our methodology actually develops a offline experience trajectory collection and then learn from the offline experience trajectory to a optimal inference control policy. So the notation is a little bit complicated, but the idea is we will use a fitted queue iteration on the semi-Markov decision process. And this Q function estimated from the experience trajectory is not only the reward information, it also consists of the uncertainty of the delay time, and it also consists of what is the quality of your underlying decision-making process in the diffusion model. So we can derive some theorem, try to characterize what is the performance guarantee of this inference control policy learning process. And it actually consists of three terms. The first term is the expert demonstration, and this expert demonstration is used to train the diffusion policy. And the second term is the diffusion model imitation error. So diffusion model is not always a perfect model. It will try to imitate the expert demonstration, but up to some error. And the last quantity is the fitted queue iteration error, because we are collecting some data or some trajectory, try to learn what is the optimal inference policy. Therefore, it has some statistical error because we are not getting exactly the environment transitions. So we can also embed this type of fitted queue offline policy inference policy learning into a online loop. And the idea is try to encourage better exploration of the experience trajectories so that it can have better and better performance when we accumulate more and more experience trajectories. So let me try to show you the performance in the kinetic environment. So in the kinetics environment, it is a 2D physics-based control tasks platform. And the goal is try to make the green and the blue ball touch or the object touch, but there's a constraint that the green object cannot touch the red thing. So red thing can be this type of surface, red thing can be this another ball. So we implement our learned inference control policy with a learned diffusion policy. And we will try to consider a very diverse set of the delay distributions. For example, it is just a constant delay or it is a random delay. And by exclusive testing, we will see that the upper row is try to use our learned inference control policy, and the lower one is some like a very naive way of doing inference. So when a inference returns, we will start another inference immediately, so which is called RTC immediate. So we will see that using our control, the success rate actually boosted quite significant, quite visibly. And there's also a very comprehensive comparison to other type of like heuristic inference or action generation policies. Like we can wait and then we can try to do other type of like uniform decision on the action generation time. And using the learned policy always improves the success rate in each of the tasks. And there's also an interesting side effect of doing the policy inference timing control. So we see that by implementing our controlled learned inference policy, we can save on average 30% of the computational cost. So this means we are reducing over 30% average diffusion model generation computation resources compared to, for example, immediate action generation. But we at the same time achieve better and better performance. So let me quickly summarize what we talked about today. So we present a training-free reward steering method for diffusion models that can adjust the diffusion generation towards high reward actions. And we also introduce a meta control of when to generate actions so that we can get better performance and also save computational resources. So jointly, I think this is a kind of like a very interesting view of generative decision making. So we are not making a simple reparameterization of the policy class, but we will try to make this type of reparameterization to be a controllable components so that we can get a integrated and reliable real-time decision system. So there are quite a lot of like open directions. For example, in the reward steering, we might need to do some type of variance reduction if at the initial stage, the hitting of the desired region E is kind of like very rare. And there's also very like broad possibilities of using the semi-Markov decision process to do the meta control for not only inference timing, but how long we should generate a action sequence and how should we refresh the action buffer. So hopefully, I think this can deliver you a new view or a idea into how to integrate a generative model into decision making. So thank you everyone for your attention, and I'm happy to take questions.
Yeah, thank you very much. Any questions?